All right, right now we're going to talk about the fundamental theorem of calculus. Now, you may remember from a previous video I said I'm going to leave out a proof. That was actually part one of the fundamental theorem of calculus that I left out. I think that showing you this proof, actually this is an application as well, so it's a proof kind of intertwined with an application, but I think we'll get at the point of the other proof that I skipped much better than the other proof would have. So, and I'll sum that up at the end of this video. But let's start off. You should have already done the exploration, the fundamental theorem of calculus exploration. And since you already did that, then you should know, or at least have an idea of something called an accumulation or an area function. An accumulation or an area function, we'll just stick with accumulation function, I guess. An accumulation function is a function whose input is any x value, and whose output is an area under a particular curve. Now, a couple things to note here. Notice that x, the independent variable, is the top portion of the integral. The integrand, the thing in the integral, the function, is in terms of t. The reason for that is we can't have x here and here. Otherwise, whatever you plugged in here would also go inside of the function, resulting in a constant inside of the integral. That's not what we want. We want the area under this curve. When we first defined the definite integral, we talked about how this variable was not really that important. It just had to match with the differential. Excuse me. So let's move on from here. Let's look at a specific area function. All right, so, and this is one I think you may have looked at actually in the exploration. So it should be familiar to you. And if it isn't, that's okay. Maybe I've got the function wrong in my head. But anyway, it is g of x equals 0, the integral from 0 to x of cosine t dt. Okay, and we want to figure out what is g of the following. So what is g of 0, g of pi over 6, and g of pi over 2. Okay, so that's what we want to know. Let's go figure that stuff out. First of all, let's look at a sketch of each one here. So this is the first part of a cosine curve. First piece of it that's above the x-axis goes to pi over 2. All right, and we'll draw that 3 times. Whoop. And then the last one, all right, better teacher would have given you a printout that had those sketched already. All right, we are going to now take and evaluate g of 0. So g of 0 would equal the integral from 0 to 0. Notice that the bottom constant here doesn't change. So the integral from 0 to 0 of f of t dt. I'm sorry, of a cosine. All right, and that's just the integral from 0 to 0. In other words, it's this area that's shaded here, which you can see is nothing. So that area is 0. That value is 0. So the value of g of 0 is 0, right? Next one, g of pi over 6. Okay, well, pi over 6 is partway down the x-axis, so we'd be trying to evaluate this area. G of pi over 6 would be the integral from 0 to pi over 6 of cosine of t dt. And if you figure that out, if we were to antiderive cosine, we would get sine of t, and we would evaluate that from 0 to pi over 6. And so we would end up with g of pi over 6 being sine of pi over 6 minus sine of 0. That turns out to be 1/2. Okay, so the area under here is 1/2. G of pi over 6 is 1/2. Last one. All the way to pi over 2 then. G of pi over 2 is going to be the integral from 0 to pi over 2 of sine of t dt. Nope, sorry. Cosine of t dt. And so that area is equal to 1 when you do the math, okay? So there's an application of an area function. And I show this for a couple of reasons. One, to show you how it works, but two, to convince you that this is a perfectly legitimate function. It's built weird, but it certainly has the features that it has every input, or you can put in really any number that you want, and you can compute outputs, it's definitely a legitimate function. Area function is a legitimate function. So kind of sear that into your mind. Sometimes students will be like, well, that's not really a function. It's like they do the same thing with piecewise functions, but no, it's really a function. Okay. All right. So here's what we just established. We could evaluate this function, especially let's look at this example here. Any number we put in here, we could evaluate it by taking the antiderivative and evaluating from the lower bound to the upper bound. All right. What if instead we tried to just take g of x on its own, the integral from 0 to x of cosine t dt, and what if we tried to just evaluate this expression? No number in here for x, just evaluate the expression. If we did that, here's what we would get. We would get sine of t, that's the antiderivative of cosine, evaluated from 0 to x. All right. And if we did that, then we would plug in the top, plug in the bottom, all right, and we would end up with sine of x, because sine of 0 is 0. So we can then write this, that g of x is equal to the integral of cosine, the integral from 0 to x of cosine t dt, that's equal to sine of x. In other words, g of x is equal to sine of x. Interesting. All right, let's see if we can play around with that and learn some more about integration and differentiation. So let's start. So let's start with this. G of x is equal to the integral 0 to x cosine t dt. All right. Now, if I've convinced you that g of x, an area function, is a perfectly legitimate function, then a perfectly legitimate question to ask about it would be, what's its derivative? What's the rate of change of g of x? So in other words, we could say, well, what is the derivative of this integral function? The derivative with respect to x of both the left and the right. Well, on the left, you would get g prime of x. We'll just write that. Okay. On the right, we get the derivative, so we'll write this out, d dx of, the integral from 0 to x cosine t dt. Okay, but we just played around with this on the previous line, or the previous page, and we got that that would be the derivative of sine of t evaluated from 0 to x. And we just showed this on the previous page, that that would be the derivative of sine of t evaluated from 0 to x would be sine of x minus sine of 0. Now, it happens to be that sine of 0 is 0, but that won't always be the case, right? We could pick a different function where this would not just be 0. However, let's suppose that we went, instead of from 0 to x, we went from 2 to x, right? So we wanted sine of 2 right here. Sine of 2 would just stay in the expression. But when we derive sine of x and whatever this constant is, the derivative will always go to 0 here, no matter what it is. Okay? So the derivative of sine of x, we can figure that out. That's cosine of x. And then the derivative of sine of 0 is just going to be 0. And again, that would work for any constant here. So the derivative of, I should have written this out, I'm sorry. I'll write this out. Excuse me. That would be the derivative of sine of x. So in other words, we can write this, that g prime of x is equal to the derivative of sine, which is cosine of x. Oh, hey, isn't that interesting? Cosine of x happened to be the integrand, right? With a different variable. All right, so what does this tell us? It tells us that differentiation and integration are inverses of each other. They undo each other. So what I did here is I took the derivative of an integral and was left with just the inside of the integral, thereby showing that they're inverses. All right, let me show you another example here just to reiterate another specific example. So that's not even really a proof, right? Because that's just using a specific example, but we could certainly generalize it. Okay, so let's take the derivative of this integral function, this area function. The integral from 1 to x of 4t cubed dt. Now, you might just jump straight to this being 4x cubed, but just to kind of hammer this home in your mind, this would be the derivative of, if we were to antiderive this, we would get t to the 4th evaluated from 1 to x. And then that would be d dx of x to the 4th minus 1 to the 4th. And when you derive this, you will get 4x cubed. Derivative of 1 is 0, so you just get 4x cubed. Again, you notice here, that is what the integrand is, with x as a variable. Okay, so again, this shows that the derivative and that differentiation and integration are inverses of each other. Okay, so the last thing that I want to do is summarize all of this, and then that'll be it for this video. And we'll do some examples of how this might be applied. Okay, so here are 3 very important things that we can derive from this. So just to summarize, so we can summarize this generally. If I take the derivative with respect to x of an area function from a to x of f of t dt, I get back f of x. Okay. All right, so 3 very important points from this. Point number 1, every continuous function is a derivative of some other function. Excuse me. Every continuous function has an antiderivative. Every continuous function has an antiderivative. And last, integration and differentiation are inverses of each other. Okay, so 3 important points here.